the weekend ever.
Yeah, it's like
And then looking at
so far behind.
our plan for the course, so next Thursday, I'll hand out the final to take home final. And the last day of the course is on the 22nd, Thursday, so 2 weeks from now, will be the last night. And that's when you turn in your final. And I looked over the final again, and there's no calculus. There's tough problems, but there's no calculus. There you go. Anyways, but tonight's stuff actually there is some calculus material with tonight's stuff. For me, it's the fun calculus stuff. So, and it actually will reinforce the stuff that you guys learned in the past. I think it's kind of, again, I think it's kind of fun stuff. There. Oh, one other thing. I don't know if you noticed that. Coursework commencement, I might try to do the estimating course.
What?
So but I'm going to do it as a, so that's an elective. It's actually the first course in the construction management degree minor. And so I've had a lot of requests for it, but it would be all done by basically a special operator. So there wouldn't be in-class lecture on it. I was looking at all my materials from the past, and I think I can do it. Pretty good that way, actually. Yeah, that's the plan. So that means you. Look at this, Michelle's going to graduate in the middle of May. Maybe, right? Middle of May.
It's all on your shoulders.
It's all baked in. We shall see. We shall see. So, that's the plan next month. But it would be it would be a special offering, so there won't be in-class lectures. Yes?
If I want to take that as a special offering, but I can't take it in April, can I?
Yeah, that's the cool thing about it.
Cool.
I'm trying to set it up so that there is certain courses that you can basically take anytime. That's what I'm trying to do.
Awesome, thank you.
But it takes a while. There's certain courses that don't work well with like the heavy stuff, like statics or dynamics type courses. I think you need actually other people around you, and kind of a collaborative learning environment to do that. That one's the construction estimating works really well, kind of like the software courses. It works really well to do it that way. All right, that's the plan. We shall see. We'll get started with chapter 10. So chapter 10, I have actually broken it up because it's like chapter 9, chapter 10 is monstrous. I've actually broken it up into 4 sections. This is huge, right? So talking about the moment of inertia, mass moment of inertia. What is inertia? What is the moment of inertia? And you've probably heard me describe it to you in the past. It's a measure of resistance to rotation about an axis. So if you had more moment of inertia, it'd be harder to get something, accelerate something, rotating, rotational acceleration. It'd be harder to get it to accelerate or decelerate, right? Because you have all that inertia behind it. It would be hard to decelerate it as well as hard to accelerate it if it had a higher moment of inertia. And it's really an unusual, I mean, you just look at the units, length to the fourth, meters to the fourth. What is that, right? I mean, you can't describe that. You're used to, cubic feet, for example, which is volume, or cubic meters, the volume. But feet to the fourth power, what is that, right? Well, it is the units of inertia. And then there's another concept called mass moment of inertia, where you take into account the basically the density of the object. So just as an example, to understand what we're talking about, let's just say we had an object and we somehow have it connected and it has a certain amount of area or volume, And we decide to rotate it about this, looks like this axis, this arbitrary axis, OO. And if it has a certain amount of area, or let's just say it's a volume, it's a sphere or something, or ellipse type of sphere. And we can go about and we can calculate its moment of inertia around this axis, let's say right here. And then you take into account its density. Well, what would happen if that sphere, or that ellipsoid sphere, what would happen if it's made out of balsa wood as opposed to made out of lead? So mass moment of inertia takes into account the density as well. So here we are, we're talking about moment of inertia is a measure of resistance to rotation, right? But if I'm taking a balsa wood sphere and I'm starting to spin it with my hands, it's pretty easy to do that. It's also pretty easy to slow it down too, right? Let's just say if I have that same sphere and it's made out of lead or gold, and I've got it hanging from a cable, and with my hands, I try to spin it, right? Well, it has a lot more resistance to accelerating or decelerating. Maybe after I get it spinning really fast, I put my hands on it and try to stop it. Well, it yanks me around because it has so much mass behind it. So mass moment of inertia is something that we need to discuss as well. But you can see that you have the same object with a different density. It could have the same moment of inertia without considering the density of it, but its mass moment of inertia could be radically different. I hope so.
Oh, okay.
I don't know if I am, actually. It's a good question. Yes, I am, thank you. Whew, that's good stuff, that's good stuff. So that's kind of the first video that talks about the difference between the mass moment of inertia and the area moment of inertia. Right now, we are covering area moment of inertia. But it's important just to understand the difference between it and to start discussing that. I think later on in the same chapter we get back to mass moment of inertia again.
So area equals density.
Mass moment of inertia.
Mass.
So mass would take into account density as well, whereas just basically the moment of inertia alone doesn't take that into account. It's just a measure of resistance. Anyways, let's look at that video. Where it will be explained again. In different terms, probably better terms.
And our favorite little lady friend?
She's
Is it her?
awesome. It's my favorite. To me, she makes a lot of sense. I hope she does to you guys too. Oh, because I'm trying to remember. That would be snow. How about running off my hard drive? Success. Awesome success.
In this video, we will introduce mass
That's
moment
away.
of inertia and area moment of inertia. The calculation of the area moment of inertia will be shown in some examples in the next video. Some students find these concepts very abstract and difficult to understand. By introducing them together, I hope it will help you to understand these concepts. But before that, I want you to pause for a moment and think. What does the word inertia mean?
Does it mean measure resistance to rotation about an axis, or
Yeah.
just a measure of resistance to motion, just in general? Because inertia doesn't necessarily have to be rotation.
Or acceleration.
It could just be in linear too.
Change in motion,
Change in motion, I like that. That's probably the best way to say it.
because it could already be in motion.
Correct, you're absolutely right. Newton's law. Newton's laws, absolutely. In fact, she uses Newton's second law to explain things in a few moments, so good thing that you bring
In
that
what
up.
capacity have you already known about inertia? When you think about it, what physical quantity comes to mind? The answer is, inertia is the resistance of an object to changes in its state of motion, and the physical quantity that you are already familiar with is mass. But what causes motion? We know that force causes translational motion, while moment causes rotational motion. According to Newton's second law, force equals to mass times linear acceleration. Or it can be written this way, that the acceleration A is caused by force F, and it equals to F divided by the mass of the object, m. As you can see, here, mass is the resistance to translational motion. And that's why sometimes mass is also called inertia mass. And since moment causes rotation, can we write something similar and relate moment to the rotational motion of an object? Indeed, we can. Similar to Newton's second law, moment equals to Im times the angular acceleration alpha. As you can see, moment and angular acceleration are both vectors and they have the same direction. Again, we can rewrite this equation into this form, and if you compare it to the equation above, you can tell that this term, Im, is the resistance to rotation, and it is known as the mass moment of inertia. Note that I put the subscript m here because I will also discuss area moment of inertia in this same video, and I want you to be able to distinguish between them. But oftentimes you will see it without the subscript m. How is it defined? Just like a moment caused by a force, the moment of inertia is always calculated about an axis, say axis AA. On the rigid body, for an arbitrary differential element with the mass dm, we can find the perpendicular distance between it and the axis, r. And the mass moment of inertia about this particular axis AA is the integration of r squared times dm integrated throughout the entire body. So unlike mass, which is absolute, mass moments of inertia is relevant, and it's different when calculated about the different axes.
So, in other words, if we get this same object further away from that axis, and you're trying to spin it around that axis, your moment of inertia is getting higher the farther you're getting away, because it is going to be much harder to rotate that around when it is further away. That is the whole concept about having a flywheel, right? You want to try to get as much mass as you can as far away from the rotation point, and that's what she's talking about. It is relative, not relevant, but relative to the axis. How far are you away from it?
Needless to say, in this moment equation, these two must be calculated about the same axis. So that's the mass moment of inertia. What about the area moment of inertia? We know that for an object with certain mass, if it has uniform density ρ, then mass equals to ρ times the volume V, and we can use a volume to represent the object. And if the volume has one uniform dimension, say uniform height h, then V is h times the cross-sectional area A, and we can use the area to represent the object. The area can be considered as a geometric reduction of the object. Similarly,
basically, we can pull the density out, we can pull the height out of it. If it's a consistent height, if it's a consistent shape, then we can describe it mathematically as an area with a density and height as well. We can describe it as an area, and we can actually calculate as an area. That's where she's leading us.
If the object has a mass moment of inertia calculated about a specified axis, because dm equals to density ρ times the differential volume dv, then this can be written as constant ρ times integration of r squared dv.
So do you see how she took the little piece of mass of each individual little piece of mass all added up is what that dm is going to do for you, right? And integrating dm. But you can take dm and you could pull the density out of it, and then you would be left with a little bit of volume. The density is constant, right? So if we're trying to find the moment of inertia of this big mass, if we want to, we can pull the density out because the density is constant. We're left with the volume. Well, guess what? We can also pull out the height as well, and we could do this in terms of just area, the little square of area. and we're gonna pull out the height as a constant as well. It's just a number, right? If the height is constant, if it's 5 tall, for example, why not pull it out as a number?
Throughout the volume of the object. And again, for constant height h, we can pull this constant outside the integration sign and get this, which is the area moment of inertia.
So the difference is what Sheila's talking about at the very beginning there. The difference is mass, and mass is related to the density. So we can pull, if we can pull the density out, we can pull the height out. We could actually think of everything in terms of areas and do math. Actually, it's going to be a lot easier doing math in terms of just area, 2-dimensional.
Mass can be reduced to a 2D geometric representation, the area. And similarly, mass moment of inertia can be reduced to a 2D geometric representation, the area moment of inertia. I will give examples in the next 2 videos on how to calculate the area moment of inertia. But before that, I want to remind you that a lot of concepts are easier to understand if you consider them as counterparts. The first row of this table deals with translational motion, and the second row deals with rotational motion. For the driving force, we have force versus moment of the force. For displacement, we have linear displacement s versus angular displacement theta, which is an angle. For velocity, we have linear velocity v versus angular velocity omega. For acceleration, we have linear acceleration a versus angular acceleration alpha. For inertia or resistance to motion, we have mass versus mass moment of inertia. And lastly, for the 2D geometric reduction of inertia, we have area versus the area moment of inertia. Hopefully, this table can help you better understand the concepts of moments of inertia.
Yes, yeah, that's kind of cool how she laid that out in terms of linear. And a lot of the calcs that we've done in the past, the statics 1, for example, we went through all those phases. Force equals mass times acceleration. And then we had displacement curves, velocity, sorry, not curves, well, actually, it's an equation. Displacement equation, velocity equation, acceleration equation, and we learned that we could do integration and differentiation to go back and forth between them. Then we also defined things in terms of mass and acceleration. Force equals mass times acceleration. Moment equals inertial mass times acceleration. That's really actually right there, acceleration. So force equals mass times acceleration. Moment equals mass moment inertia times acceleration. So you actually see, and we actually went through a whole chapter where we did things in terms of angular rotation. I think that was the statics 1, actually. Angle and radians, and then velocities, angular velocity and angular acceleration. Neat little table, actually. All right. Going back to my little PowerPoint. So pretty much all the problems that we do tonight and the homework is all figuring out the area moment of inertia. A 2-dimensional flat object trying to figure out what its area is. And of course it's underneath a curve, so you're using calculus to figure, and specifically integration to figure out the area underneath that curve. We can look up the value for the moment of inertia from tables. So if I have a disk, for example, there, disk or solid cylinder. You can barely read it. 1/2 mass times radius squared. That should be the same here. Yep. If you're rotating around the z-axis, that is. If this is indeed the z-axis, 1/2 mass times the radius squared. But what's interesting is what would happen if you rotated that same disk instead of around its center, if you will. Instead, you rotate it like laterally around, this would be the x-axis, or say the y-axis. Well, it is a quarter mass times radius squared when you rotate it either x or y-axis instead of the z. Interestingly, though, that you can actually discover what the moment of inertia is around the z-axis by just adding. If it is a symmetric object like this is, if you know what the moment of inertia is around the x-axis plus the moment of inertia around the y-axis, you could add them together. Say Ix is equal to quarter mass times radius squared plus another quarter times mass times radius squared. A quarter and a quarter adds up to a half, 1/2. So it's very interesting because it is symmetric and identical both ways that this actually works out for a disk or for a cylinder. The polar moment of inertia can be discovered by figuring out the moment of inertia going the opposite way. You're always used to seeing cylinders or disks being rotated in a record player type way around the z-axis. And notice how we can solve for that. The integration of, in the x, the integration of y squared, whatever your equation is, y squared times every little piece of area. And we are actually going to use this equation in a few minutes to actually figure out the moment of inertia around a different axis. And it's what I like about it. For me, this is the fun and easy part of integration in calculus. You're integrating from 0 to 2, and you know what you're doing. The other day, the stuff that we were doing was much more difficult, the integration we were doing. This one's pretty straightforward. I'll walk you through it. And it's repeatable. You do the same thing over and over again. So we can calculate, say, this sphere. This sphere right here has a hollow sphere. The moment of inertia is 2/3 mass times radius squared. Then there's something called the parallel axis theorem. If you know what the moment of inertia is, say, spinning it around its center axis, if you know what that is, you can actually figure out what the moment of inertia is if you move it away. If you have a parallel axis, if you actually move the object away, and then you're trying to figure out what it would take to what its moment of inertia would be around, rather than having it together. So the distance that we see between the two parallel axes, if you know what the moment of inertia of one object is, and you translate it away but still rotate it around, the distance between the center to center distance, you can still figure out what the moment of inertia is. So here's how you do it. Whatever the moment of inertia was originally when you were spinning it around the center axis, plus whatever the area is, so it's a circle, right? Times the distance out to it, squared times the distance out to it. Actually, this one right here is the one that we end up using for this case. So this is like rotating it around the z-axis. So the area times whatever that distance is between the two. It's called the parallel axis theorem. It actually works out really well, and we're gonna use it. So if you could figure out what the moment of inertia is if it was, say, spinning around its center axis right in the middle, and if you move it away, you could still figure out what its moment of inertia is, as long as you know the distance between as long as it's a parallel axis and you know the distance between those axi. It's still discoverable. Radius of gyration describes the distribution of area. All right, think about it. If you had a solid cylinder, how would it be different than say a hoop, which is basically a cylinder with another cylinder subtracted out of the center of it? There would be, and this would be pretty much like a flywheel, like the old-fashioned flywheels, where they try to get as little material on the center, and they try to get as much mass and material as far away from the center as they can. So this would be, turns out the material or the mass that's the furthest away from the rotation actually makes the most, provides the most inertia, if you will. Of course, that's the whole theory behind a flywheel. So if we take that in, we take that into account, another concept comes up called the radius of gyration, which takes into account where the material lies. Because we could have the same amount of material, but spread it out and actually have a farther radius out. Instead of having any material in the middle, maybe we just don't have any material in the middle, or just barely enough to make a little fan in the middle, and then you have most of your material on this outer rim. Well, the radius of gyration is K, is a way to determine the relationship between the moment of inertia and the area that you have. Describes the distribution of cross-sectional area around the centroidal axis. And the unit is just in length. Do you see that radius? The radius is in terms of K. I don't even know if I have a problem. I don't think I have a single radius of gyration. Just conceptual, that's all we do. And there's a video that talks a little bit more about it.
In this video, we will learn how to calculate the